So today I'm going to talk about the windings further, and we're going to talk about a distribution factor and other factors that account for the difference in the induced voltage if you were to calculate the or measure the voltage from a phase of the windings. So previously we've looked at this from this Fourier series analysis, and now I'm going to connect the analysis with the factors. So we looked at the pitch factor last time, and so now I'm going to look at the distribution factor. So if we look at the winding where we had one slight shorting, then we're actually going to get a reduction in the voltage, induced voltage, because unlike if the phase or the set of coils was overlapping like this, when we shift one coil relative to the other, we're going to create a phase shift in the induced voltages, and so that reduces down the magnitude of the voltage. But it also, doing this, actually improves the harmonics, reduces down the higher harmonics. So it has some good effects, but the negative is the peak voltage drops. So we looked at this using Fourier series. So now we can also look at this using a distribution factor and connect the two approaches. So if we so let me just write a few things. Distribution factor. So in general, if the winding for one phase group so if this would be a phase group, so it's a set of coils. I'll talk more. I'll give an example of phase group more in a minute. But for now, just think of it as this set of coils here. So if in general, if the winding for one phase group connected in series, so then each of these sets of coils, these phase groups, would have a voltage associated with it, induced voltage, back EMF voltage, and so then they would sum up to be some total. So if there's this phase shift due to the windings being moved relative to each other by one slot, in this case one shorting slot, then there's going to be a difference in the voltage. So the voltage induced in each winding EC will be phase shifted by the slot pitch gamma. This will reduce the magnitude of the induced voltage. So we can assume the voltage in each phase, it's each coil is in each phase shifted coil is EC. Then when I put phase, I don't mean like three-phase, I mean angular shift phase angle. Phase shifted coil is EC. Then the total voltage in the phase group is going to be E sub PG. So only if all windings are in the same slot will there be no phase shift. So what we could write is we have some voltage induced, and due to the rotor magnets, for example, rotating past the windings, that will induce some voltage. So that voltage will be a summation of the number of shifts. In this case, there's one. It's one slot shift. So the way that I'm going to define this would be a 2, and then EC will be the number of the number of voltages that are created across each coil. So we could draw this. So we would have some total, and so in this, I should have given an example with two shifts. This one's only got one shift. And this, so if we have the phase group is shifted by two phase angles, so two slots, then we'd have a summation of the voltage on each coil. So we'd have 3 coils, and the 3 coils are shifted by some angle. I guess I could draw that on here, and then they'd sum up to this total. So the question is, how does the total sum of the winding voltage relate to the individual voltage across each of the coils? So let's calculate this. In this example, we have 3 coils, and they're shifted by a phase angle. So how is EC, the voltage on one coil, and the total phase group voltage related? So we can do some mathematics to figure that out. So we can. So again, I'm keeping it with 3 coils. So each coil will have a voltage, and that voltage will be phase shifted relative to the total. So we could draw this as so we could define this as gamma, which is the phase shift for one slot. So this is gamma. And I better put it this takes a bit of drawing. So we've got these 3 voltages. How is EC related to EPG? It's a geometric problem here. So we could choose the center point for each of these 3 voltages, and then we could draw a line coming down. I've got the angle. The angle is not going to work in that example. Sorry. Let me do that again. I think it would be easier to have a I should have had a printout for this. It looks a lot simpler in my on my page. So this is EC, EC, EC. This is EPG. Okay, so then this is a right angle here. That's supposed to be a right angle also. Okay, and so these 3 lines are going to have the same length, and then this is gamma, gamma. Okay, so if we can take we can also take these points down like that, and can draw up to here. And choose that as A. We can choose this as B, and we can choose this point as C, like that. Okay? A, B, C. So if we take that, so if we take those 3 points and draw them like so, C, A, B, and so this, so at this point here we can call D. Okay, so this is B, A, C, and then in the middle is D. D. Then this is alpha here, okay? Then, and this is 90 degrees. Then, if this is alpha and this is 90 degrees, the angle here is going to be 90 minus alpha. And then this angle here is alpha over 2, and this is alpha over 2. So coming back over here, this will be 90. This will be 90 minus alpha, and this is alpha. Is that right? So then we and that's L there. This is L. So then oh boy. EPG, half EPG, oh dear. Okay, yeah. So then that gives these angles. This point here is going to be half EPG from here to here. So this is half EPG from this point to this point. This is L. So then, and then if this point from this point here to this point here is half EPG, and each one of these is alpha over 2, then if we go all the way round, there has to be a total from here to here of NP alpha. So half of that is NP alpha over 2. So then we have I think I'll send you I'm going to make a handout of this. I'm pretty sure I've confused you. So this from here to here is EPG over 2. This is L. This part here is NP alpha over 2. So then we end up with half EPG is equal to this is EPG over 2. half EPG, and this is L. So, and this is the angle. So we can find the length here is equal to L sine NP alpha over 2. Okay, and then also we get out half EC is equal to L sine alpha 2, where from this point here to this point here, so this whole length here is EC. So half of it will be from here to here. This is half EC. That length there is related to the length L by the sine of alpha over 2. So L sine alpha over 2 will give you the EC over 2. So we get this relating the EC to the sine alpha over 2, and then half of the total length of the angles is NP alpha over 2. So with these two relationships, we can write thus: EPG divided by EC is equal to sine NP alpha over 2 divided by sine alpha over 2. I'll make a handout that more clearly shows that, because it's difficult to draw it there. Okay, so that relates the total phasor voltage for one phase group to the individual voltage over one coil. Okay, so then with this, so hence the induced voltage would be EC. So we had EC times a distribution factor times N, the number of coils that are shifted. So if we look at this equation here, we can write it in this form. So then we'd have EC, so we could multiply the top and bottom by NP. EC NP sine NP alpha over 2 divided by NP sine alpha over 2. In this formula, where they have the distribution factor, the convention is to put NP outside of it. But then, in order to get it in that form, we have to multiply these two together. We put an NP on the top and the bottom, and so therefore, so then hence, if we compare, then the pitch factor. So in order for the pitch factor to be defined, then the pitch factor will be everything other than this NP here, and the EC. So the pitch factor is sine NP alpha over 2 divided by NP sine alpha 2. Gamma, sorry, gamma. I haven't had much sleep lately. Sorry. This is the distribution. Factor. Thank you. Gamma, not alpha. Okay, so now with this distribution factor, we have two factors that affect the voltage that we've now looked at. We've got the pitch factor and the distribution factor. So the induced RMS that we wrote out before, we can now add this distribution factor. So that's the distribution, and this is the pitch distribution. So let's now look at this again with respect to the Fourier series analysis that we did. And that's where this is quite interesting. So there's this geometric relationship between the voltages for the whole set of winding group and the voltage. So how does that relate with regard to the Fourier series analysis for the different windings we looked at? So we've looked at four different windings. So we had, and so I'll try to summarize it here. So winding function, and then we have the Fourier series that it corresponds to. So we looked at one slot per pole per phase with no chorting, and we had a square wave. And so then we had the pitch factor and the slot factor with the coil pitch was the same as the pole pitch. Coil pitch and pole pitch were the same. And so then we had the Fourier series that we obtained, and for the fundamental, it's just the square function. So that gives so now we can look at what that gives with regard to the pitch factor and the distribution factor, how this relates to the Fourier series, because they should connect. So in this example, for the first one, they were both 1 because the W and TP the same, and there's no chorting. Then we looked at what happens if we had 2 slots per pole per phase, and then what we got was a winding where W and TP were not the same. W. So the pole pitch and the coil pitch were different, and that gave us a winding function that was given by this here, where when we compare, we can see we have this additional sine 5 pi over 12 for the fundamental. remember the pitch factor and the distribution factor, they're worked out for the fundamental. So we didn't have any chorting. We didn't have where the coils were shifted by one slot pitch. So so this is now sine 5 pi over 12, and this is 1. And then the third one, we had 2 slots per pole per phase, and then we had 1 slot chorting. And so it looks something like this. So then in that case, we have 4, this is where it's kind of interesting. We derived that we had cosine pi over 12 squared times sine theta, and so on. But now there's the cosine squared. That's not in the form of the. It's not in this form. Well, we don't have any sines. That's what I'm saying. This is cosine, so we can convert that to sines. Because pi over 12 is the same as cosine pi over 12 is the same as sine 5 pi over 12 squared. And so this then works out, it's sine squared for the case where we have 2 slots per pole per phase and 1 slot shorting. So in this case we have sine 5 pi over 12, and this is also sine 5 pi over 12. We can check that with our formula. So for this example here, we had 12 slots. So gamma was 30 degrees. We had 1 slot that was 1 slot shorting. That means the NP is 2. If it's 1, there's no shorting, and you just get so if you put a 1 in here, you can see they just get a 1 out. This is NP here. So when we put this into here, we get out 0.9659, which is actually equal to putting gamma in here, we're going to get pi over 12, and NP is 2. So when we do that, this is actually equal to sine 5 pi over 12, which is actually simpler looking. And then the fourth. Does that make sense? So what I'm trying to show here is that the pitch factor and distribution factor, they can be calculated from the from these equations that we derived, or they come out from the Fourier analysis directly. The fourth winding that we looked at was the 2 slot per pole per phase with 2 slots of shorting. So then we had this nice waveform like this. So this was 2 slots per pole per phase and 2 slot shorting. So then we derived that the winding function was given by this here, which had the cosine terms in it, like that. So it turns out that, so we can, cosine pi over 12 is sine 5 pi over 12, and then this is sine 4 pi over 12. But that, so we can put that in here, sine 4 pi over 12, sine 5 pi over 12 times sine theta, and so on. Now, this is where it's kind of interesting. If we now calculate the distribution factor for this one, we have I better write this. What's NP going to be? Remember how we got this? We have 4 windings. Remember? So it's going to be 4, essentially. So then, and then alpha was 30 degrees because there were 12 slots. So with that, we can put in the distribution factor terms. So MP is 4, and we get out that KD is equal to 0.8365. Now, but this is pretty. It's kind of interesting. If you look at this here, if you could put it in your calculator, sine 5 pi over 12 is equal to, because see this is sine 4 pi over 12 here, sine 4 pi over 12, it's the same. So I checked it, but maybe you should check it too because I haven't had enough sleep. This bottom one here, 1 over 4 times sine pi over 12 is equal to sine 5 pi over 12. It's kind of interesting geometric thing that. So it's the same, gives the same number, 0.8365. If you check check your notes. So for the fourth case, the pitch factor is 1, and this is sine 4 pi over 12 divided by 4 sine pi over 12. Okay, that took longer than I thought. I guess I'll stop. And do you have any questions on that? So now, hopefully, this has connected 2 different things. The Fourier analysis allows you to study any winding. The winding function analysis. The winding function analysis allows you to study any type of winding in a methodical way, the pitch factor and the distribution factor allow you to get the magnitudes for the windings, but they, in my opinion, somewhat cloud what's going on compared to the Fourier analysis. So after the break, I'll talk about winding connections and two other factors we have to take into account. Okay, thanks.